Okay, we're going to find the integration by substitution. So this is when we find the integral of a composite function, so a function inside of a function. So if g is the inside function of whose range is over the interval I, and if f, the outside function, is continuous on that same interval, then g, the inside function, is, and if g, the inside function, is differentiable on this interval, then the antiderivative of big F, then big F is the antiderivative of f on that interval, then we can say that the integral of f of g of x times g prime of x dx. Notice that we're given that g of x is our inside function and g prime of x is our derivative of our inside function. This is simply equal to the antiderivative of g of x plus c. Now this is often called u-substitution because what we usually do is we make the inside function equal to u. And if we let the inside function equal to u, then if we take the derivative of u with respect to x, we get g prime of x. And if I solve this differential for du, I get du is equal to g prime of x dx. And so you go back to your original equation, replace the g prime of x dx with du, and replace the g of x with u. We can rewrite this integral as the integral of f of u du. And so therefore, all I have to do is find the integral of the antiderivative of f of u. So we're going to evaluate each of these indefinite integrals. So first thing I notice is that x squared plus 1 is an inside function. So I need to let u equal x squared plus 1. Now I'm going to find the derivative of u with respect to x, which will be 2x dx, 2x, and then do the differential. I see that du is equal to 2x dx. Now, conveniently, that our 2x dx is given to us in our problem, so we can rewrite this as the integral of u squared du. And then we just integrate u squared, which is 1/3 u cubed plus c, and then finally go back to your original variable, replacing every u with x squared plus 1 to get our final answer. That's how you do the integration by u substitution. All right, I want you to try the next one. This time our inside function was 5u, so we're going to let 5x. We're going to let u equal 5x. So derivative of u with respect to x would be 5. So therefore du is equal to 5 times dx. And we were given 5 and dx. And they're not by each other, but that's okay because remember, it doesn't matter which order with multiplication. So I can replace the 5x with u and the 5dx with du. Integrating that, the integral of cosine, remember, is sine of u plus c, and then go back to my original variable, replacing the u with 5x. So my answer to this integral problem is sine of 5x plus c. All right, I'm going to do another example for you. Looking at example B, I need to identify my inside function. Well, my inside function is x cubed plus 1. So I'm going to let u equal x cubed plus 1. And then I want to find the derivative of u with respect to x, and that would be 3x squared. And then do the differential, du is equal to 3x squared dx. So I'm going to replace my original integral problem, the yellow highlighted, the x cubed plus 1 with u, and then the orange highlighted with du. And then I'm going to integrate this, and so that's going to be 2/3 u to the 3/2 plus c, which is 2/3, and u, we have to go back to our x variable, remember, is x cubed plus 1 to the 3/2 plus c, which gives us 2/3 the square root of 3x plus 1 quantity cubed plus c. All right, I want you to try the next example. First thing I notice is I have an inside function. So I'm going to start by letting u equal my inside function of x squared. So the derivative of u is equal to 2x dx. Notice I did my 2 steps in one on that derivative. If you want to go straight to the differential like I did here, you feel free to do that. And so we noticed that we can replace 2x dx in our original problem with du, and we can replace x squared with u. So I have the integral of sine of u du, which is negative cosine of u plus c, which is negative cosine of x squared plus c as my answer. Okay, so notice I have the inside function of u squared plus 1. So I know that we're going to let u equal x squared plus 1. So find the differential, du is equal to 2x dx. But notice I do not have 2x dx to substitute in to write the du. There's something missing. All I have is the dx and the x. So in this case, what's the best thing to do is just to solve this differential equation for dx. I'm going to solve du equals 2x dx for dx. And so the best way to do that is just divide each side by 2x. Okay. Now I'm going to substitute into our original equation what we found dx to equal, which is du divided by 2x, and what we let u equal, which is x squared plus 1. So I have x, u squared, and in place of that dx, du over 2x. And then simplify down. So I'm going to combine my like terms. So the x and the du over 2x are common, so I'll put those together. And then notice I have x in the numerator, x in the denominator, so I can cancel that out. And so this actually just becomes the integral of 1/2 u squared du. And now I have it all in one variable, so I can finally integrate. And I can factor out that 1/2. And the integral of u squared we know to be 1/3 u cubed. And then we multiply that together. I get 1/6 u, which remember is x squared plus 1, quantity cubed plus c. And that would be our integral of this problem. All right, you try the next one. So we know our inside function is x squared plus 1, so we're going to let u equal x squared plus 1. And then we find the derivative of u, which would be 2x dx. Now I don't have 2x dx, so I'm going to get dx by itself, and so that dx is going to be equal to du divided by 2x. So we have u to the 4th x. Replace that dx with du over 2x. Simplify that down, and I end up with the integral of 1/2 u to the 4th d. Factoring out the 1/2, and then finding the integral of u to the 4th, which is 1/5 u to the 5th, plus c. Multiplying 1/2 times 1/5 gives us 1/10, replacing u with x squared plus 1 to the 5th plus c. Similarly, on this problem, notice my inside function is 4x cubed minus 9, so I'm going to let u equal 4x cubed minus 9. If I differentiate this, I find that du is equal to 12x squared dx, but that's not what's given, so I'm going to solve this differential equation for dx, which gives us du divided by 12x squared. So going back to my original problem, I can replace the 4x cubed minus 9 with u, and I can replace the dx with du over 12x squared. Simplifying down this problem, the x squares cancel out, and 6 divided by 12 simplifies down to 1/2. So I'm left with 1/2, and then I'm going to move that u up so I can integrate it, so that's 1/2 u to the negative 3 du. Okay, factoring out the 1/2, I can just find the integral of u to the negative 3, which is negative 1/2 u to the negative 2 power, which gives us negative 1/4, and then u to the negative 2 power. Remember, u is 4x cubed minus 9. And then getting rid of our negative exponents, we bring that 4x cubed minus 9 down to the denominator and raise it to the square power. And that is our final answer. Okay, you try this next example. Start by identifying your inside function, which is simply du plus u is 3x minus 1, so du equals 3x, so dx is equal to du divided by 3. So I have u to the 1/2 du divided by 3, or 1/3 u to the 1/2 du. Integrating that, I get 2/9 u to the 3/2. Remember, u is x squared, 3x minus 1, plus c, which is 2/3 of 3x minus 1, quantity cubed, and then the square root of that. Okay, another type of integration by substitution might show up is, what if your x's don't cancel out and you end up with more than one variable? And then you have to use a process called the change of variable. I'll show you how this is done. So notice our inside function on this example is 2x minus 1. So we let u equal 2x minus 1. We find the derivative of u, which is just 2 dx. And again, I don't have 2 dx to substitute in, so I'm going to get dx by itself, which is du divided by 2. But notice when I do all my substitution, I still have x times u to the 1/2 times du over 2. The x did not cancel out. When the x does not cancel out, I cannot integrate this now because it's integrating with respect of du, but I have to have that only the u variable. So to fix that, I go back up to where we defined u. We defined u as 2x minus 1. We're going to solve this equation for x. So u is equal to 2x minus 1. Solving for x, I'm going to add the 1 to each side and then divide each side by 2. So x is equal to u plus 1 divided by 2. So I'm going to replace the x with u plus 1 divided by 2. Now I have all of the u variable, but before I integrate, I want to simplify this down. So 1/2 times that 2 on the bottom gives us 1/4. Then I have u plus 1, and I still need to multiply that by u to the 1/2. Remember, we do not have a product rule of integration, so I need to multiply it out. So I'm going to distribute that u to the 1/2 to each term in the parentheses to get u to the 3/2 plus u to the 1/4. Notice I took out my constant. And so now I'm ready to integrate. So I got the 1/4, u to the, adding 1 power, that's going to be 5/2. And so that means I need to multiply that term by 2/5. plus, and then if I take u to the 1/2 plus 1 gives us 3/2, so I need to multiply that term by 2/3 plus c. Okay, notice that the 1/4 is times by all of this, so be careful. I almost forgot my parentheses here, and I might have only distributed that 1/4 to that first term, but it's that 1/4 is times by our entire antiderivative. So that gives us 1/10 u, which we know to be 2x minus 1 to the 5/2 power, plus 1/6 of u, which is 2x minus 1 to the 3/2 power, plus c. Now you can go back to your integrals here, but when it gets messy like this and you have multiple terms, they tend to let you keep it in fraction powers and not having to go back to the original form of integrals. Actually, no, don't try this one. I'm going to work it out because this is the first time we have two inside functions. And so I think I'll work this example without having you do it. Okay, so the first thing you want to do is you want to rewrite this integral of sine to the 3x quantity squared times cosine of 3x dx, so that you see that you have two inside functions. 3x is inside the sine function, but sine of 3x is inside of the square function. So I'm going to let u equal my most outer inside function. So u is equal to sine of 3x. So the derivative of u with respect to x is going to be cosine of 3x, but use the chain rule, times by the derivative of the inside, which is 3, then our dx. Now notice again, I don't quite have that in our given information. So I need to rewrite this differential equation as dx divided by 3 is equal to cosine of 3x dx, or you could have got the x by itself, but notice I'm going to replace cosine of 3x dx. I'm going to show you another way of doing this with du over 3. And I'm going to replace sine of 3x with u. So it gives us u squared du over 3, or 1/3 times the integral of u squared du. And all I have to do is now integrate u squared, which is 1/3 u cubed, plus c, or 1/9 u, which we know to be sine of 3x, quantity cubed, plus 3, but it's a trig function, so we would write this as 1/9 sine cubed of 3x plus c. And that's how you do if you have multiple inside functions. All right, now our next section here, and again, I'm going to do this example here. Now we're going to talk about what to do if we have definite integrals. How does that change? Well, the main difference with integrating by definite integrals and by indefinite integrals with u-substitution is that you must remember to change your upper and lower bounds. We're rewriting our function in terms of u, so our upper and lower bounds has to be changed in terms of u as well. So let me show you how that would work. So first thing, we would identify our inside function, which in this case, our inside function is simply x squared plus 1. So we're going to let u equal x squared plus 1. So derivative of u would be, therefore, 2x dx. That's not what we have, so I'm going to rewrite that. X dx on side by itself, so du divided by 2 is equal to x dx, another way of doing this substitution here. And so now I've substituted in place of the x squared plus 1 as u, so that gives me u cubed, and replacing the x dx with du over 2. But I cannot integrate this yet because I need to make this a definite integral. And so now that my variable is u, my upper and lower bounds need to be in terms of u as well. And our original upper and lower bounds were in terms of 0 and 1. So let's figure out what our upper and lower bounds are. So to find our new upper bound, I'm going to take my old upper bound, which was 1, and substitute in place of every x in my u statement. So basically, I'm going to find u of 1. So u of 1 is 1 squared plus 1, since u is defined as x squared plus 1, which gives us 2. So my new upper bound is 2. To find my new lower bound, I do the same thing. So I go to my u function and I replace every x with 0. So I'm going to find u of 0, which gives us 1. So our lower bound is now 1. So this is the integral from 1 to 2 of 1/2 u cubed du. So let's integrate that. So the 1/2 comes out, and remember the integral of u cubed is 1/4 u to the 4th. We're going to evaluate this from 1 to 2, or 1/8 u to the 4th, evaluate it from 1 to 2. Which, okay, remember definite integrals where you place u with 2, and then we minus replacing u with 1. So big F of the upper bound minus the big F of the lower bound, f of b minus f of a. Simplifying this down, I get 15/8 as my definite integral. Okay, I want you to try this next example here, doing our definite integral. So identify your inside function. So we're going to let u equal 2x minus 1, and the derivative of u is going to be 2 dx. So I need to get dx by itself, so that's going to be du divided by 2 is equal to dx. And I have an x left over, so I need to solve my u equation for x. And I get x is equal to u plus 1 over 2. So now I need to find my new upper bound. So I need to figure out u of 5. So that's 2 times 5 minus 1, replacing every x with 5 in my u statement. And then finding my lower bound, replacing every x with 1 in my u statement. And I get the integral from 1 to 9 of, we're going to replace our 2x minus 1 with u. We're going to place our x with u plus 1 over 2. We're going to place our dx with du over 2. Ooh, that was a lot of substitution. Okay, and so now we're just going to simplify this because it's kind of messy as it is. Bring in that fraction power up and making it negative, and I still need to multiply by 1/2 du. So that gives us 1/4. And then I have u plus 1 times u to the negative 1/2 du. Now again, remember, no product rule for integration. And so before I integrate this, I need to figure out what u plus 1 times u to the negative 1/2 is. So I'm going to just do the distributive property and get u to the 1/2 plus u to the negative 1/2 du. Notice I factored out my constant. And so now the antiderivative of u to the 1/2 is 2/3 u to the 3/2, and the antiderivative of u to the negative 1/2 is 2u to the 1/2. And I'm going to evaluate this from 1 to 9. Substituting in 9 in place of every u. And then that, subtract, substituting 1 in place of every u. And all of that is times by 1/4. So first we got to figure out what 9 to the 3/2 is. Okay, so that's the square root of 9, which is square root of 9 quantity cubed. And so square root of 9 is 3, so it's actually just 3 cubed, which is 27. And then we take 27 times by 2/3. And then that gives us 6. And then just 1 to the power is just going to be 2/3 plus 2. All right, let's do a little bit more simplifying here on the inside functions. I get 18 plus 6, distributing the negative, I get negative 2/3 minus 2 to the 1/4. 18 plus 6 minus 2 minus 2/3 gives us 66/3 minus 2/3, which is 64/3 times 1/4, which then again simplifies down to simply 16/3. Okay, the last thing I want to learn about in this lesson is the integrals of even and odd functions. Now, these rules here for the integration of the even and odd function only works if you're integrating over a closed interval from negative a to a. So negative 2 to 2, or negative 5 to 5, or negative 6 to 6. So this rule only applies if you're doing a definite integral and your upper and lower bounds are exact opposites of each other. So if f happens to be an even function, then the integral from negative a to a of f of x dx is 2 times the integral of 0 to a of f of x dx. And we do this because sometimes it's a lot easy to do definite integrals where one of the bounds is 0. It's much easier to work out. Now, the odd one is even nicer. If f is an odd function, the integral from negative a to a of f of x dx is just 0, because you have the same amount on the below the x-axis as above the x-axis, so the area becomes 0. All right, so let's try an example here. So first thing you have to do is remember, how do we figure out if a function is even or odd? Now remember, to figure out if a function is even or odd, you just replace every variable with the opposite. So we know, let's let f of x equal my function here, which is sine of cubed x. Sine cubed x cosine x plus sine x cosine x. And then to figure out if it's even or odd, I'm going to find f of negative x. Now, we remember that sine is an odd function. So sine of negative x is negative sine of x, and negative sine of x cubed is negative sine cubed of x. And we know cosine is an even function, so cosine of negative x is just cosine of x. And so then that gives us plus a negative sine of x, because it's odd, times cosine of x, because cosine is even. Then if we factor out a negative, we get sine cubed x cosine x plus sine x cosine x. And notice that our answer is the exact opposite of our original function. We had negative times f of x, so it's the exact opposite of our original, which tells me that this is an odd function. And since this is the odd function, the integral from negative pi over 2 to pi over 2 of an odd function is 0. Okay, you try the next one. So the first thing I notice is our integral, or integrating from negative cosine of x to pi over 4 to pi over 4, so negative a to a. So I remember that my inside function, which is cosine of negative x, is an even function. So I can rewrite this as the integral of 0 to pi over 4 cosine of x and double that answer. So the integral of cosine, remember, is simply sine of x. I'm going to evaluate that 0 to pi over 4. So 2 times sine of pi over 4 minus sine of 0. Using my unit circle knowledge, I know the sine of pi over 4 is square root of 2 over 2, and I know that the sine of 0 degrees is 0. And so that gives us 2 times the square root of 2, or just square root of 2. Okay, try this one. So upper and lower bounds are exact opposites, and my function f of x is sine of x cosine of x. So I want to figure out what f of negative x is. So replacing every x with negative x and simplifying down. Well, sine of negative x is equal to negative sine of x, and cosine of negative x is simply cosine of x. So comparing this to my original problem, I see it's the exact opposite of the original problem, which means that this is an odd function. Since it's an odd function, the integral from negative pi over 2 to pi over 2 of an odd function is 0.